So this afternoon, we're going to look at some practical ways in which we can trap some of these errors and biases that I've been talking about earlier. And some of the methods that I'm going to introduce to you might seem very obvious and very simple, but I still think that being able to inspect data and find errors within the data is a very powerful skill to have, no matter what stage of your research career, whether you're just beginning your PhD, whether you're like me 30 years into my research career. Being able to look at data and understand where there might be problems is a very powerful skill to have. It's useful, obviously, for our own research. It's useful for checking and peer reviewing papers and manuscripts that others might send us. And it's especially useful for checking data sets that other people have created. And only last week, I was looking at some data from the United Nations, who you would think would provide very reliable data. And I think I found an error in some of their population statistics. So I've written to the UN and said, I think this value doesn't look right. Can you tell me what's going on? So we just have to approach data with that kind of critical mind. So in the lecture this morning, I covered a range of things that can go wrong from the very beginning of the information flow to the end of it. And when we look at data, it is helpful to have that idea of an information flow in your mind. So you can think, okay, where might a problem have arisen in this continuum from the collection of the data to how we're trying to use it today. What we're going to do in the exercise is essentially looking at data, visually inspecting it, and applying some simple tests to determine whether or not there are errors in basic rainfall and maybe temperature data if we have time. And as before, if you've got any questions, then please do just put your hand up or put your mic on and ask your question, or post the question in the chat box. But let's just see how much you were listening to me this morning. I've got a little quiz here for you, and I'll give you a chance to perhaps look at the question and discuss it with your neighbor. If you're in the lab, I can see some of you are in the lab. Why not talk to your neighbor what you think the answer might be? And this will hopefully reinforce some of the points that were made this morning. All right, are you ready? So let's see if anyone can get maximum points. Question 1. The hydromet information flow begins with, is it A, careful calibration of equipment, B, a clear set of objectives for gathering data and monitoring networks, C, careful selection of sites for installing hydromet equipment, or all of the above? So I'm going to give you 30 seconds each time to chat with your neighbor, see what you think. Write the answer down, and then we'll go through the answer. Okay, let's see in the chat. Okay, so anyone feel super confident about this first question, just to get things going? Please put.
Can you look in the chat room?
I'm struggling to see the chat box whilst I'm presenting, I'm afraid.
Yes, it seems that we have answers.
Okay, if you could read them out for me.
Yes,
What
everybody took D.
to D?
D, yes.
D for dad or B for bottle?
D for dad.
D for dad.
Yeah.
Okay. Here's the answer. Actually, all of these other points are important. It is important to ensure that the equipment is carefully calibrated. It's also very important to ensure that stations and where we're undertaking the observations are appropriate. But all of these things depend on what we're trying to achieve from the research. What is the research goal or objective? That defines where you locate the equipment, the type of equipment you need, and how often you need to calibrate it, download the data, and so forth. So having those clear objectives is the first step. All right, ready for question 2. Which of the following are potential sources of bias and or errors in river discharge records? Is it A, changes in river channel cross-section at gauge sites, changes in river gauging methods or equipment, changes in upstream water diversions and abstractions? Or is it D, all of the above? What do you think? Oh,
Can you see?
I gave you a quick clue there then. So what did you think? Did you all think that it's D?
Yes.
Does that make sense? Yes?
Yes.
So you remember from this morning, if the channel cross-section is unstable, then that changes the relationship between the water depth and the amount of water in the channel. If we change, for example, from doing manual measurements through to fixed instruments in the stream, that can cause a change. If there's a dam or some other change in the catchment upstream, like a land use change or a water diversion, that can also affect the river flow record. So river flow records are just subject to all sorts of uncertainties, and we need to keep these in mind when we're using river flow data in our research. All right, how about this one? Now, this is a tricky question. So, which of the following is not caused by human biases? A tendency to underreport small daily rainfall totals, a tendency to over-report rainfalls that are divisible by 5, tendency to underreport the amount of snowfall, tendency to underreport rainfall on weekends and holidays. Right, I'm going to try not to press the wrong button this time, so I don't give you the answer. See what you think. Chat to your neighbour.
Okay, so we have a number of C's mostly, and a 1B, if I'm correct.
Okay, well done everyone who thought it was C. Okay, very good. So yes, when we see manually collected rainfall records, people can be variously relaxed about whether or not to record a trace amount of rainfall. So there's a tendency to have too few small rainfall amounts. That's quite a common issue in rainfall records. I showed you during the lecture how if you look at a histogram of rainfall data, you find peaks at 5, 10, 15, 20, and that's a very, very common issue, very common. And I also explained why for parts of Europe, North America, Australia, there tends to be fewer rain days on weekends because people are less inclined to go to the weather station on their day off. Okay, and these are just very human factors that affect the rainfall record. The tendency to underreport the amount of snowfall is more to do with the equipment. It's still, even in the 21st century, actually quite hard to measure snowfall accurately. And so you're right, the majority of you got C, I think. Okay, question 4. Which of the following statements is true? Data from automatic weather stations is always more reliable than data collected manually. There are few weather stations above 5,000 meters. Most automatic weather stations measure precipitation. There's always enough solar energy to power an automatic weather station. So here we're thinking about some of the practicalities of the type of instrument that you can see in the picture. What do you think the answer is?
Is there only one answer, or?
Yes.
Yes.
Okay, do we have any answers?
Yes, the majority, I think everyone selected B, and we have 3 C's. So we have quite a number of C's.
Okay, all right, good. A good.
No, it was the previous question. Sorry. I think B is the most.
Okay, all right. Well, very well done, everyone. Absolutely. A is not right because automatic weather stations bring with them all sorts of their own difficulties. So just because it's an automatic system doesn't mean to say it's any worse or better than a human-based system. For C, actually, very few, relatively few automatic weather stations do measure precipitation. Most of them are measuring things like temperature, wind speed, and direction. And as I explained in the lecture, sometimes these weather stations can run out of electricity because there's not enough sunshine to keep the batteries charged. So well done to everyone who thought it was B. Worldwide, there are very, very few weather stations above 5,000 meters. And yet, this is the parts of the world where some of the most rapid and dramatic climate change impacts are taking place in terms of melting of snow and ice and impacts on glaciers. And so we have this paradox of some of the most rapid environmental changes occurring in places where we have the least information. There's a genuine data scarcity in these places. Okay, last question then. Which of the following can be used to detect errors in hydrometric data? Comparison of records from neighboring stations, graphical inspection and analysis of data, careful reference to station metadata, all of the above.
So we have now varying answers, B and D.
B and B
Yeah.
and D. Okay.
Slightly more D's, I think.
All right, and the correct answer is D.
Yeah.
Okay, so one way in which we can find errors is by comparing data sets from neighboring sites, because you'd expect them to be behaving in a very similar fashion. So if one suddenly diverts from the other, then that could be caused by an error. as I've already shown you, just looking at graphs for outliers and unusual patterns is a very powerful way of spotting an error. And also having reference to information about the weather station, whether it's been moved in terms of its position, its height, changes in the instruments or the observers. These are important factors too. Okay, so did anyone get 5 out of 5? No?
I think I skipped the first question, but the rest I did correct, I think so.
Okay, so I'll give you 4 out of 5. So that means that it's still worth staying for the next part of the exercise. Okay, here we go then. All right, so I'm going to show you now some images of some instruments, and I would like you to write down what you think the instruments are being used to measure and what you think could be the issues at the particular site that I'm going to show you. Okay, and let's see if I can also just change my graph so I can see the chat box at the same time. This is, here we go. Let's see. Okay. No, that's unfortunate. Okay, let's try that again. Sorry guys, it really doesn't want to show me the chat box. So if someone in the room can read out again what the answers are, that'd be really good.
Sure.
Okay.
Yes.
Okay, yeah, sorry about this. Right then, first thing, what's being measured here and what might be some of the issues at this site, which is very high up, I think, in the Colorado Rocky Mountains. Any thoughts? Okay, so any thoughts? What might be some of the issues with this site? Any ideas?
Okay, so I will try to read some answers.
Yeah.
Milica, problem could be strong wind. Rasko, avalanche or glacier moving could damage gauge. Or maybe you want to read your own answers. You can unmute yourself by pressing space and then read your answer. Maybe it will be better. So we can start with Christina, perhaps, and go everyone to give their answers.
Yeah, thank you. That'd be nice.
Christina. Okay, so.
Well, I think the place is inaccessible for measurements because it is running on a high altitude.
Okay, I think I caught that. Were you saying that because of the high altitude, there's the difficulty of access to this site?
Yes.
Yeah, very good. Yeah, so you can see here how you can just imagine how hard it would be to climb up the mountain on a regular basis in these conditions, especially in winter, to collect the data, to make these kinds of conventional manual measurements. So yeah, absolutely, access, the difficult terrain is a key factor, and that's partly why there are so few of these sorts of stations in the world. Okay, thank you, very good. Any other answers?
Branislav, perhaps?
Well, I think spaces are.
Unmute. No.
Well, I think the lack of sunshine could be the problem if the station is powered by solar panels.
Okay, yeah. If you had an automatic weather station located here, because of the high altitude, the likelihood of lots of clouds, snowstorms, that could be a problem for the solar panels and the energy supply. So you're absolutely right. Anyone else?
So, Rasko?
And extreme events like, oh, sorry. And extreme events like avalanche, or if glacier moving can damage the gauges, or some extreme wind or some extreme storms could also damage the gauges, so that could be also a problem.
Yeah, excellent. They're all very good answers. So yes, rock falls can cause damage. Very high wind speeds can destroy the equipment. And even in these sorts of locations, you can have problems with lightning strikes. So in the Rocky Mountains, at certain times of the day, it's extremely dangerous to go to the summit of a mountain. So lightning can be a serious issue. And then finally, you know, if we're imagining trying to measure snowfall using this sort of gauge or precipitation, it's so high above the ground that the amount of snowfall that you would catch here would be way too small, especially in windy conditions. All right, very good. Let's move to the second case. Now, can anyone actually tell me what this instrument is measuring before we go any further?
Okay. Please feel free to
maybe evaporation.
Could you just repeat that for me so I can hear better?
Unmute. Yes, we have an answer.
Evaporation. Yes, very good. So this is a quite a traditional way of measuring evaporation, where you literally keep a water level. You measure the water level in these tanks each day to very precise levels, and the amount of water that drops gives you a handle on the amount of evaporation. So what are the sorts of things that can go wrong with this kind of instrument, do you think?
Okay. Please feel free to join the conversation.
So maybe this.
Okay.
Maybe the plants can make some shape. I don't know if you hear me. Maybe these plants growing can make some shape.
Oh, plants? Are you saying plants could shade this?
Yes, I said
Yeah.
maybe they can remove these plants.
Yes.
If I may say so, I think the pools are made of metal as well.
Okay, so we've got a number of issues here then. So actually, if you could mute your microphone, that'll. Thank you. Thank you. So there's some issues here with the metal that affects the heating of the instrument. Someone explained that, you know, the shading perhaps by vegetation could affect the evaporation. But the reason the metal cage is here is because of something quite simple and obvious, that in a semi-arid environment where there's very little water, birds and other animals will come to this site, and birds and animals can affect the water level. Some animals may be drinking from this and so forth. So you just have those very simple practical issues that can affect what you're actually measuring on the ground. Right, what about this one? What's the problem here? This is a weather station that is apparently located in a car park on a university campus in the US. Any thoughts?
Concrete or asphalt.
Yeah, very good. So the concrete and the asphalt will clearly increase the temperature in the compound and will have a really big effect on any temperature measures that are taken from within this Stevenson screen. Okay. This one I think we've already talked about a little bit. You know, measurements on glaciers and in other unstable environments are quite difficult to do, as illustrated in this case. Now, this is a really, I think, quite a tricky one. Can anyone tell me what you think is being measured here and what might the problem be at this particular site? Any thoughts?
Can somebody please read the chat?
Thank you.
Yeah. Do you want me to do it?
Yes, if you could, that'd be great. Because
Okay,
I can see you now. Yeah.
We have underground water, and we have, is it measuring the water level in the reservoir and the vicinity of water surface?
Okay. Okay. I think there's some partial answers there. So this is actually measuring the water level in the river. Okay. So in here, in this tube will be a float that goes up and down with the water level, and that float activates a mechanism with a pen or a digital recorder to measure the height of the flow of the river. The only problem, well, a problem with this site is that at very high flows, water will get trapped behind this bridge and will artificially be elevated by the bridge, especially if trees and other debris comes down the river, gets caught on the bridge. That can cause the water level to be increased artificially at this site. So this is a really nice example of a very poorly located river gauging station. So if you ever in your research or your careers, if you ever go and see a site like this, then you should be telling the authorities this is no use at all. Okay, last one. Now this is a tricky one. What is this instrument measuring, and what do you think might be the problems here?
We have one answer.
Okay, if you could, someone could read out some answers for me, that'd be great. Is it Tiana?
Yeah, I'm home,
yeah, thank you.
so I don't have that problem with. Yeah, so it's a heliograph, and the absence of grass is the problem.
Okay, so a heliograph, that's to measure the amount of sunshine hours, because this glass sphere acts as a magnifying glass, and it focuses the sun's ray on a piece of card behind, and it gradually burns a line in the card. So when the light is strong enough, it burns a line, and we can measure the duration of sunshine hours. I'm not sure that the concrete in this case is necessarily an issue for this instrument, but the problem might be is deciding when does the burnt piece of card begin and end. So where is it partially burnt, or what if the sun goes behind a cloud and it stops for a little bit? It's very hard to actually convert the length of the burn line into a precise measure of the duration of sunshine hours. Okay, but also, of course, if you have nearby structures that are interfering with the sunlight, so putting the instrument in shade at any point in the day, then that could be a problem too. And I can see here, for example, that there is this pole. Maybe part of the day that pole is casting a shadow over the instrument. All right. Okay, very good. I don't think we need a break. So if it's okay with you, we'll carry on to the next step of the exercise. This, by the way, is a picture just outside my village. So hopefully when some of you come to England, you can see some of our wonderful countryside. Right. How do we check for data errors when we look at the raw data? Here are some of the top tips that I've picked up over the years. And this table, I hope if you're able to, it might be useful to print this off, because it's a good checklist of things we should be looking out for when we're looking at a new data set. So first of all, when we look at the length of the record, are there the correct number of days or the correct number of hours? If you've got 10 years of data with 2 leap years within it, have you got 3,652 days? That's a very first and simple check. Is the length of the data set what you expect? Next thing we should be doing is just looking at the time series to see where there are any outliers and the range of the data, and to see if that variation is constant in time, or whether there's anything strange in the data like we looked at this morning. Secondly, you know, what are the codes that are being used to represent a missing data value? How are commas or decimal points being used? Is the decimalization correct? Let's take a look at the most extreme values. Are they within a range that you would kind of expect for the location? So having a sense of what might be a realistic value is always a useful thing. Are there any biases like I showed you this morning? So for example, too few rain days on a Sunday and more rainfall than you'd expect on a Monday. Are there more 5s and 10s than you'd expect? And this is perhaps the simplest check of all, and you'd be amazed how often you find data sets where, for example, the maximum temperature recorded in the data is less than the minimum. So it's obviously it can't be. It just can't be. So that's a very good check. Looking at the range of the values, say between the maximum and the minimum, can sometimes tell us if the instrument has been moved, say from a shaded location to an unshaded one. That will show up in the range of the data. Also, are the changes that we see in the data from one day to the next, is that a realistic jump in temperature from one day to the next? And finally, do we see the same value occurring lots of times in a row? And that's especially a warning flag for rainfall if we see exactly the same value in 2 or more days in a row, because statistically that's very unlikely for rainfall. Okay, so there's sort of some basic checks for you to think about. Now let's just look at some examples of how this plays out. So if we look at these example data, if you look at on the left hand side, the column, all the values are 5. So and this is for a temperature record. So you would ask yourself, is it reasonable for the temperature record to be the same value for day after day after day? Probably not. Okay, and then we can see in the middle column that suddenly the temperatures go from these single values to ones where you've got more variation. Now this is starting to look more credible, isn't it? So why do you think, what do you think has gone on in this data set? Have you got any ideas? How could this error have occurred? Any thoughts? If there's anything in the chat, if someone could read that out for me, that'd be great.
So it says, I think, change of metric system, and I think someone has rounded up or down the decimal values, perhaps. Yeah, so they're all reasonable suggestions, and one could be that a data variable has got muddled up. So this sequence of values could be, for example, cloud cover in octas, or as you suggested, someone's, the values have been misentered, miscoded in some way, or we're missing a decimal place, or the data were uploaded and information was lost. Okay, then if we look at the final column, and these are temperatures, what, if anything, stands out to you here? Any thoughts? I just entered the high value. I see here is 74.8. That doesn't seem right. That's it. So that's brilliant. So you've used the common sense that what is a credible upper temperature value. So we might in Yemen expect some highs of around 40, but not really 50s, 70s, and 60s. So something has really gone wrong in here somewhere. Now, again, we look at these data and one might think, well, perhaps this isn't actually temperature, but someone has entered the humidity values
as if they are temperature. So relative humidity could vary in this sort of range. How would we go and check which of those ideas is correct? What would be the best thing to do? I mean, it might be difficult in Yemen now, obviously, because of the conflict and all the other problems that Yemen is facing. But what would you be able to do in other circumstances?
So we have an answer. Look at the metadata if it exists.
That's it. Yeah, go back to the original data sheets and see what data were recorded on these particular days in these dates, and to see what's going on, and then to try and understand the cause of the root of the problem, so then you're able to resolve it. So once again, yeah, looking at the raw data, sometimes in the handwritten format, is a very powerful thing to do. Okay, now chance for you to look at a whole year's worth of temperature data. And can you, I'll give you 30 seconds, can you quickly scan those data and tell me if there's anything in there that doesn't look quite right? Maybe, yeah, use the chat function if there's anything that you think is not looking correct. So keep in mind, these are temperature data, daily temperature data for the year 2014. Any thoughts?
I think everybody saw the December 27th.
Also, the whole December is higher than the rest.
And we have one more answer. Missing values are not flagged properly.
Okay, so where do people think there are missing data in this record?
I'm not sure. Can you perhaps elaborate, Julia, about the missing flag?
Yeah, can you hear me well?
Yes,
yes, yeah, very good, thanks.
Yeah, so end of February, 29, 30, 31st. Also, oh, actually, I'm sorry. It's all the days that that are not actually existing. But I'm assuming that the computer or an Excel spreadsheet might flag this as missing data and put 0. I'm not sure what the processing method is, but I'm assuming that it would be automatically filled in with 0, which is not.
You're absolutely right that is always an error to be really alert to, is what happens in these sorts of circumstances. Are they left? Are the data left blank? Is a missing data code entered there, or in the worst case, a 0? So you're absolutely right to always be checking that the number of days in a given month or a year are matching what you would expect to see. So well done. So in terms of any of the numbers, are there numbers in there that you think aren't right?
We have high values for December 27th. I think everybody recognizes this.
This one here.
Yes.
Yeah, that one. Yeah, of a temperature of 47.1 degrees Celsius in December would be a special day, wouldn't it? That would be a very hot day. So you're absolutely right. So what do you think the true value might have been, looking at the neighboring values?
4.7.
4.7 would be a fair estimate. Okay, and there are other values in here. So this one here, that is probably 35.5, 30 or something like that. Okay, we can only guess, but these are two examples of clear data entry errors, and if we hadn't picked them up, this value would have emerged from our automatic script as the annual maximum temperature. Okay, so if we were then analyzing changes in extremes from one year to the next, all of a sudden we have just picked up an extreme value that is a nonsense. So that's why this is so important. Okay, how about this spreadsheet? What's going on here? This is rainfall for the year 2000. What's the problem?
Why not? Why not?
Well, maybe either the missing data is flagged as 0, or maybe people have, or computer had rounded the numbers to 0, if it's, for example, 0.5 or something like that.
Yeah.
In some cases.
Yeah, absolutely. Thank you for that. Yeah. So
it will be much easier for us to think if you know the
yeah.
If we know the geographical position of the gauge, we would have more to think, how to say. If you know where is this
the location of the location.
If you know the location, it will be easier to think, how to say.
Yeah, that's a fair point. That there are obviously some parts of the world where it is possible to have 3 months with no rainfall whatsoever.
Okay.
This was not the case in the case of this weather station, which is in Central Asia. So we've got this example of zeros being used as missing data values, but also for actual rainfall values. So we've got a mix of the two treatments there. The other thing we have is that even if we accept that these are all missing values, we can see that here they've missed the leap day. So there are too few days in February if you scan back and forth. Okay, so checking for leap days is a really useful thing, because that can lead to all sorts of nasty errors further down the line. Okay, one last one for you to look at then. How about this? Take a few seconds to look at this. This is a much more subtle set of errors here. Okay, anyone spot anything in here that they thought looks a bit suspect?
(26th and 27th of March, they have the same values.
Yeah, very good. Someone's got a really sharp eye to spot that. Okay, well done, whoever found that, because this is it's possible in a large amount of data to have the same value in two consecutive days. It's more likely for temperature that the 2 days will be the same, but for rainfall, because it's so much more variable, to have 2 days with the same amount to 1/10 of a millimeter, you would want to check that. And as before, you would want to check that these 0 values for 2 whole months are correct as well, going back to the data sheets. So you get the sense of what we're up to. And this morning I gave you these examples where plotting a time series plot gives you a very quick view of obvious outliers. Using histograms, plotting the frequency of certain values can reveal the 5, 10 and other number biases. Like here we can see, I mentioned before, there's lots of zeros but very few little numbers before you then get these spikes at 5 and 10 millimeters. So histogram plots are a very powerful way of looking at the data for checking for that. And histograms can also reveal big outliers. So if we look at these temperature data here, you can see the bulk of the data lies between the range of 8 to 28 degrees, but you've got these very low values and these super high values. And one way in which automatic systems can check for this is to calculate the mean and then to look for 4 standard deviations from the mean, because that should capture just virtually the whole data set. So anything that lies 3 or 4 standard deviations from the mean is going to be a real outlier like these. So once you've picked these up, then you can you're better able to say, do I believe this value? What are the physical processes that could have given a temperature this high in this data set? So you're asking those questions as you look at the data. Here's another example of a temperature data set where you've got just this one outlier here, which is possibly a missing data code that's been set to 0 rather than some other value like -999 to find the data. I mentioned as well that comparing records from neighboring sites, and here what we've got an example of 2 temperature data sets that are recorded at the same weather station but using different instruments. And what we can see is that the maximum temperature values agree very well between the tiny tag and the manual measurements undertaken by the meteorological agency. But when we look at the minimum temperature, straight away we can see there's this group of values in the manual data set which are much higher than are shown by the automatic values. So this side-by-side comparison straight away is helping us to spot problems with the data. And tomorrow we'll have an exercise to go through that correlation and side-by-side testing, if you like to join in with the advanced training session. And tomorrow I'll also be mentioning this particular test, Petit's test, which helps to spot step changes in data to see whether or not there's a break in the data which might have occurred due to a change of instrument or a moving of the weather station. So there we go. You can see a range of techniques for trapping methods, trapping data with problems. So looking at the meta information, visually inspecting the data, thinking about outliers, doing nearest neighbor analysis and day of week checks and breakpoint checks. So I suggest, if it's okay with everyone, we take a 5-minute break now, and then we'll have a look at some more data, and I'm going to give you a bit longer time to look at the actual data set. Now, if you can go to your folder, you should find a file, an Excel file with some data in it. If you can obtain that file and have that ready after the break, that would be great. So let's come back at 2:35 and continue with the exercise. Okay.
Okay, thank you. And we will have a short break.
Okay, thank you. Just before we go into the exercise, I'd just like to say a few words about where we might find lots of meteorological and hydrological data and climate model information in the public domain. Often just having access to data can be an obstacle to our research, but a year or so ago, I undertook some work with the Asian Development Bank, where they asked me to basically look all over the world for where we could find data sets in the public domain. And I've provided a link here, which will provide you with about 70 different data sets, which can be used in a whole host of climate-related research studies. So as background information, basic weather and climate information, results from climate model experiments, and some data on climate change impacts. So I just signpost this resource as a useful starting point if you're trying to look around for data sets that might already exist that you could draw in to your research. Now, this afternoon, we're going to be using a data set from one very widely used archive, the Global Summary of the Day, which provides meteorological data for stations all over the world that are listed by the World Meteorological Organization. And this interface, which you can access via the link below, enables you to search by station name, coordinates, variables, and date for data sets. So I did just that for Serbia and found some data that we're going to look at this afternoon. And it's this is a really, I think, important lesson, because this is a very widely used archive. The data are freely available, publicly available, and used a great deal in many research papers. Yet, in the next few minutes, you're going to learn quite quickly that even these sorts of data sets that are being issued by NOAA in the US can still contain a range of data issues. So just to demonstrate this, what we're looking at is the data set from Belgrade, and this has been accessed from the portal I've just shown you, and you should be able to see your Excel file. And I've just given you the raw data. Later on, I can supply you with a file with all the solutions and some of the answers that we're going to be looking for shortly. But until then, let's just take a look at the data. So can everyone confirm that you've got your Excel file open? Have you all been able to find the Excel file? If someone could confirm that either in the chat box or over the mic, that'd be great.
Everybody, do we have the file? Yes. Yes, I think we have.
Excellent. Okay, that's really good. So it should look like this. And let me just explain what we've got here. So the various columns we've got in column A, that's the code given to the Belgrade station. B is the name of the station. C and D, latitude and longitude. E is the elevation. F is the day, the date, beginning in 1st of January 1985. Then you've got the maximum, minimum temperatures. You also have rainfall data with some rainfall codes here, an average temperature at the end here. And this describes, this final column describes whether the temperature data were based on a single value in a day, or was sampled every 24 hours or every 6 hours, but we can ignore that column. Okay, so the file I've given you is literally taken from the public domain data set with no attempt by me to clean it up. So your mission is to use the little checklist that I gave you earlier to look at the record and see how many of these errors you can spot. Now I'm going to give you, let's say until 3 your time. So I'm going to give you just over 20 minutes to really dig around in this data set, see what you can find. And I don't mind if you work in teams to do this, or you share your insights with your neighbors, but just look at the Excel file, apply some of the visualization methods, maybe do some histogram plots, just to get a sense of what's going on in the data. And I'd like you to see how many problems you can find in the data set. Maybe you'll come back to me and say, this is fine. It's the data are clean. We can't spot any errors here, so we're happy to proceed with our research using this public domain data set. Okay, is that clear to everyone? If there's a question before we start, perhaps just put that in the chat box and I'll try to answer it for you. Any questions?
It seems that we don't have questions.
Okay, so what I'm going to do is I'm going to leave this screen, this checklist, checkbox up on the screen for you, and off you go. I'll just mute my microphone, and I guess the editors of this recording can chop out the next 20 minutes and then resume once we all come back as a group to share what we found. How does that sound? So I'll just stay online, and if you've got any questions, then just pop it in the into the dialog box. Now I don't want you to put the answers in just yet in the box. Just any questions. Keep a list of all the things you find, okay? And then we'll discuss them in 20 minutes time. Okay?
Okay.
Stop there wherever you are and see what we've found as a group. So for starters, let me just ask you what your overall sense of the data were and what you think might be the most serious issues with this data set. So either put that in the chat box as I can now read it, or if you'd like to speak over the microphone, then please let me know. So who'd like to go first? Any thoughts on what might be some of the big issues with this data set?
Anybody? Is it easier for you to talk or to write in the chat?
Maybe to write, because it's...
Okay, they will write it in the chat.
Yeah, if you like to put a comment in the chat box, then I can react to that, and then I will walk you through what I think are some of the issues with this data set.
Okay, thank you.
Okay, it's unclear if there are missing values. Okay, that's one to flag, isn't it? What might be the missing data code within this data set? Has Did anyone pick that up? Yeah, so you don't know whether it's 0. Yeah, so someone else. Yeah, is it Rasko? Yes. Yeah, there is a 99.99 or something like that. So that's quite a common missing data code, and you can see some instances of it. It's unlikely that you'll ever get a, well, I mean, sometime somewhere on Earth there probably has been a 99.99 millimeter rainfall event, but it's highly unlikely. So that would be a good code. 347 records, yeah, so quite a lot of missing data in there. Okay, stepping back from that information, was there anything else really a big issue? High temperature in January, missing dates, and lots of same values. Yes, I agree with that, and I'll show you some examples later on. Anything else? Yes, very well spotted. So I didn't tell you deliberately that the measurements are in Fahrenheit rather than Celsius, because it came from a US portal. So, you know, those of us in Europe are probably happier working in degrees Celsius, so we could just do the conversion for that. But then by converting between the two, there may be some rounding errors in the data as well. And you're absolutely right, the precipitation is being measured in 1/100ths of an inch to fit with the US standard, whereas we would probably be happier measuring in 0.1 millimeters, again converting between those two units. Excellent. Missing data rows for 28 to 29 and 31st of August. So is that Irina, whoever spotted that? I think that is probably the most serious issue in the data set, because if you didn't spot that error, then everything else in your analysis could be moved out of sequence by a few days. So well done for spotting that. Okay, anything else? All right, well, I think you've done really well there, given the 20 minutes. I spent nearly a day or so just sort of looking at the data and comparing it and thinking about it for this exercise, and you've done really well in just 20 minutes. So here we go. Let's just look at some of the other slides. So I can't stress how important it is to check the expected number of days. It's a really simple test, but one that can straight away reveal whether or not we've got a problem. So the data set I've given you covers these 35 years. Taking into account the leap years, we'd expect 12,783 days. And in fact, there are 4 missing values, which Irina, I think, spotted correctly. And here you can see, if we look down the date column, you can see there's just a missing rows there. So if we'd fed, for example, these data raw into a hydrological model or some other model, we would have a break in the actual data that might not match with something we're trying to simulate, which could be river flow or some ecological indicator. It's also interesting that in this period, you can see this very large rainfall total, 11.81 inches. And if we plot the time series, you can see what an outlier that is. So that occurs on the 9th of September 1993. And because of the unit conversion between the imperial and the standard measurements, that is actually 300 millimeters. So my question to you then is, do you believe that value? Is 300 millimeters of rainfall, exactly 300 millimeters of rainfall in one day, plausible for Belgrade? Any thoughts on that?
No, it's not possible. It's not possible, but in 2014, we had similar values, but for 3 days.
So when I see a value like that, 300 millimeters is a round number, isn't it? So straight away a flag goes up, and then I think, well, 300 millimeters, we have had that in one day here in the UK. The record in one day is 340 millimeters, so it's within the realms of plausibility. But it's the fact that it's a whole 300 millimeters rather than 297.8 or something like that, which makes me suspicious. So one thing we could do would be to check, say, in the newspaper archives or some other record to see, well, was there any reports in the media or in the newspapers of widespread flooding or something else that could independently corroborate whether or not that was an actual event. But I think looking at the chat box, most of you saying no chance, no way, don't believe this value. So how that value got into the data set raises some questions. And of course, if we were using this data set to analyze extreme events for design purposes, say for urban drainage systems, and we'd use this value uncritically, we would have incorporated a suspect value into our extreme value analysis. So this is why I really want to stress the importance of quality checking the extremes, especially given the nature of this, the emphasis of this overall training workshop. Okay, so we don't believe that. Now, if we move to the next slide, I don't know whether any of you had a chance to do a day of the week check. This doesn't look too bad, although if you look at the larger number of rain days on Monday, perhaps, and the relatively smaller number on Sunday, although Sunday is not the lowest in the week, maybe there is some bulking up of values on Monday and some under recording of rainfall on Sunday. The so-called Sunday effect may be evident here in terms of the lower frequency of rain days. But I've got an open mind about that one. Let's look at the next. Now, the 510 check. What do you think here? I don't know if any of you had a chance to produce a histogram. What's going on here? So we've got, I haven't bothered to convert to millimeters. I've just done all the values, the frequency of values between 0 and 1 inch. Is there or is there not a bias in the data here? Okay, so the red line denotes the expected frequency, and this is from a gamma distribution. Often we'll use a gamma distribution to represent daily rainfall totals. So if we plot the expected value from the gamma distribution against the observed frequency, and you can see very clear number bias in the data. Now, it doesn't quite sit on the sorts of numbers we're expecting because the millimeters have been converted into inches. Now, if we'd shown this in millimeters, we would show a very clear 510 number bias. So the rainfall measurers at this site over the 35-year period have definitely shown a bias towards numbers ending in 0 or 5. That, as I said before, is a very common bias that we see in rainfall data sets all over the world. It's very common indeed. And I think someone did pick up that there are successive temperature values that all look the same. Well done. And there you can see that there are successive rainfall values. Here I've done a quick check to see whether the value before is the same as the value after. False yes. And you can see here an extract for December 2001 where you've got lots of rainfall values all the same for an entire week. Or in this case here, what's the chance of 2 days each having 0.55 millimeters exactly? Is that a keystroke entry error, or was that a real event? Was it just by chance that that happened in those days? But overall, looking at the rainfall data, I think there's 135 instances where there are replicate values which we might want to check. All right, and then, although I haven't described the technique itself, I will be talking to the group tomorrow about Petit's test, which is a very simple test to undertake for using the ranking of data to look for breakpoints in time series, because if we see a breakpoint, that can indicate a change of the station, change of an instrument, change of an observer, or a change in something else to do with the site. And here you can see I've done a Petit test on the rainfall in terms of the annual total, the annual number of wet days. So these are non-zero values, and then the calculated annual mean wet day amount. And we can attach a statistical significance to each of those time series to say whether or not the difference, the step change that's identified by the technique is significant or not. And what we actually learn is that, yes, maybe the data are homogeneous in terms of the annual rainfall total because it's not varying that much. There's no marked change from one decade to the next. However, we are seeing a greater number of wet days in the most recent 20 years. And when we combine the two, because of the lower rainfall totals and the greater number of wet days, we actually have smaller rainfall amounts on average. So the mean has come down in the most recent decade. And that is, according to Petit's test, a statistically difference between these two periods. Now, tomorrow we'll be thinking about whether or not is this difference here an indication of some change in the climate of Belgrade, or is it some indication of a change in the measurement practices or quality of the data at this site? At the moment, we don't know. So if you'd like to learn more about this test, come to the advanced session tomorrow, where I'll be describing Petit's test. Also, I will put the answers to the Excel exercise into the into my folder, and maybe Biljana can share that with you, and you'll see a tab where I've done the Petit's calculation, and you can see just how simple it is to do this. And it's a very nice check for the homogeneity, the continuity of a data set. Okay, so there we go. If I was to sum up this data set against those 10 tests that I set before you, I'd say 4 days too few. There are some suspect outliers. Yes, there is a consistent missing data code for both rainfall and temperature, so that's good. Consistent use of decimals, yes. I don't think any of us really trust that 300 millimeter rainfall value, so that would warrant some further investigation. There is some day of week number bias, perhaps in the frequency of rain days. We didn't really look at the temperature data very much for this exercise, but there are 135 duplicate values in the record. So what would based on that, what would your overall assessment be? Question to you all. What's your overall assessment?
Use the data set very carefully.
Use the data set carefully. Yeah. So we could do a little bit more to clean it up, but I hope you saw that this was a useful exercise. So many of you will be using data sets, as I say, that others have prepared or in the public domain. And this is just an example. And even in 20 minutes, you've been able to establish that there are some issues with this data set. It's a nice data set to have 35 years, more or less complete, but we shouldn't just take it all on trust and analyze it, jump straight into the research without checking for ourselves the quality of the data. So I think that's a good point at which to close. From my point of view, if there are any questions now, perhaps you'd like to put any questions in the chat box, anything you'd like me to answer before we finish for today.
Yes, we have one question from Tanya. It says, after the NIMs are spotted, what would you do? Exclude or fill with some mean value?
Oh, so this, we're talking about the missing data values. Is that what we mean here?
Yes, I think so.
Yeah. So that depends on what we're using the data for. So for example, if we're using the data for continuous simulation, let's say we're taking the rainfall data to feed it and temperature data to feed into a hydrological model, then we would want to build a complete data set, and we might infill using by interpolating between the two nearest values on either side. So we might fill in that way, or we might take the average. I tend to prefer interpolation as a simple method if we're doing a time series analysis. If we're interested in, let's say, the changes in extreme, then I think we've got more of a problem, particularly with the rainfall, given that outlier, if I can find it again, it was on slide 45. There we go. So we're suspicious of this outlier. These ones maybe we're okay with. Maybe we're happy with these, so we could just filter out that suspect value or try and understand why it happened. But equally, we should check these others if we can. But you can see how your approach to the missing data will depend on the ultimate purpose of your application of the data. Okay, any other questions? Okay, well, if there are no other questions, then if you've got any further thoughts or reflections, then please do drop me an email. If you've got a question comes to you after you've thought about this a bit more, or you want to know more about the literature in this area, then please drop me a line and I can help you as best I can. I think that's probably a good place to stop then, Biljana.
Yes, we have a session at 4 for senior researchers with Manfred. And thank you, Rob, for this. This was very interesting. I hope that our students will apply for tomorrow's advanced session with you. So thank you very much. I hope that they will come up with some questions later on, and that they will have enough time to send you an email and ask you what they wanted to know. I think this can be really helpful, this exercise, because a lot of them will work with some kind of measured data during their PhD thesis preparation and defense. So I think that this will be really useful to them. But also, as you talk about fatigue tests. So in many papers I read that they use it to somehow find when the shift in data actually occurred. So they perform the trend test and then apply fatigue test or different similar tests just to see when the trend started. Is it possible to use it for detection of trend or the start of the trend, or maybe a regime shift between the two periods? Is it possible to use the test for regime shifts? We know that there are regime shifts in all different kinds of ecosystems.
Yeah.
So, yeah, thank you.
So yes, tomorrow I will talk quite a bit more about Petit's test. It's not a perfect test. So for example, if there's an underlying trend in the data, then that can cause issues with the test. But again, it depends on the hypothesis you're seeking to analyze. So for example, in the data set here, you might hypothesize that there was a change in the reliability of rainfall, or there was a change in the location of the weather station in a certain year, let's say 1999. And you could use the Petit's test to see whether or not that step change is evident in the data. But the point is that you've set up a hypothesis before you went in there and tested it. Sometimes the Petit's test can also be used to look for breakpoints in data as a preliminary screening, just to see whether there's an apparent change in the data that you might then afterwards be able to explain by reference to station metadata. I guess the sort of final remark I would make is that you know, we talked a lot about data measurements at weather stations and at river gauging stations, and maybe one thing to consider for the participants and the research students would be to actually go and visit one of these sites, to look at the instruments and to get a sense of how how easy it is for errors to occur in these locations, even in well-run, nicely instrumented compounds that comply with World Meteorological Organization standards. It's still possible for things to go wrong, and there's really no substitute for visiting, you know, spending half a day visiting such a site to get a deeper sense of the kinds of things that can go wrong with the data that we are so often using.